Right now, an average AI data center draws enough electricity to power a small city.
Yeah, it's staggering.
It really is. And as of today, April 22, 2026, out here in Las Vegas at the Google Cloud Next conference, Google has officially acknowledged a pretty harsh physical reality.
Right, which is that if the tech industry doesn't fundamentally change the physical shape and structure of its computer chips, well, the whole artificial intelligence revolution is just going to run out of power.
Literally run out of power. And that sets the stakes for today's deep dive. We are pouring through a massive stack of source material covering Google's brand new hardware announcement.
The 8th generation of their tensor processing unit.
Exactly, specifically the brand new TPU-8T and the TPU-8i. And the mission today isn't just to, read off a spec sheet. We want to figure out how Google is using these highly specialized pieces of silicon to break the physical bottlenecks of computing.
And, frankly, how they're planning to directly challenge Nvidia's massive dominance in the AI chip market.
Yeah, because we're looking at a fundamental shift in strategy here.
Oh, absolutely. Google has intentionally split their flagship production line into two entirely different physical architectures. They're completely tearing up the traditional playbook.
And the downstream effects of this hardware arms race are going to reshape the entire software industry, which is why whether you're building a scrappy startup, managing a massive enterprise infrastructure, or just using AI tools to summarize your morning emails, this shift actually matters to you.
It does. I mean, silicon chips might sound like a super dry, esoteric topic reserved for hardware engineers,
It's
but
the hidden engine, right?
yeah, it's the engine powering the new era of inference.
Because we are moving away from chatbots that just, generate text and moving toward autonomous AI agents that can actually reason, plan, execute multi-step workflows, and act on your behalf.
Right, and to pull that off, an AI agent needs to respond instantly. It needs near zero latency.
But before we get to how the new Generation 8 chips achieve that, we need to look at the physical limitation of the hardware everyone else is currently fighting over. We need to understand the mechanism that makes Google's chips so different from the standard GPUs.
The standard GPUs that are basically powering most of the tech world right now.
Okay, let's unpack this. Let's start with those standard GPUs. Graphics processing units. Nvidia makes them. The entire industry is on a massive waiting list to buy them, and they are incredibly powerful.
They are. But you have to remember what they were built for. A GPU was originally built to render graphics for video games.
Right, which requires a system to calculate millions of pixels all at the exact same time.
Exactly. That's called parallel computing. And a few years ago, researchers realized that parallel computing is also the exact mechanism needed to run an artificial intelligence model.
But a GPU, at its core, is still a general-purpose processor.
Yeah, it can render a 4K video game, it can mine cryptocurrency, and it can train a neural network. Right. Because it has to be capable of doing all those different tasks, its physical architecture is compromised. It carries overhead.
Like physically on the chip.
Right, to get the physical space on the silicon itself. Transistors are dedicated to logic paths that an AI model will literally never use.
Okay, so instead of standard analogies, let's look at it like this. A GPU is basically like a high-end Swiss Army knife.
Oh, that's a good way to put it.
Right. It's great at many things. It's highly versatile. You can take it camping and survive. But a TPU, a tensor processing unit, is like a professional chef's scalpel-sharp Santoku knife.
Yes.
It is built to do one specific crucial task with unmatched efficiency. It's terrible at everything else, but for that one job, it's perfect.
If we connect this to the bigger picture, Google realized a decade ago that as AI models grow, using general-purpose hardware like a Swiss Army knife becomes financially and energetically unsustainable.
Because of the structural specialization.
Exactly. That structural specialization is the defining characteristic of an ASIC, or an application-specific integrated circuit. A TPU is an ASIC built purely for AI.
Its physical layout is hardwired to do matrix multiplications and tensor operations.
Right.
Let's break down the actual mechanism there. What does a matrix multiplication physically look like for the chip?
Well, matrix multiplication is essentially just doing thousands of simple math problems simultaneously.
Okay.
A traditional processor takes a complex piece of math, breaks it down, and solves it step by step. But a TPU is physically wired with thousands of tiny rudimentary calculators arranged in a massive grid.
So it doesn't do complex logic at all?
Not really. It just takes a massive block of data, multiplies it by another massive block of data, and spits out the result all at the exact same instant.
Because it isn't burdened by the ability to do anything else.
Right, the efficiency is just off the charts. Google has actually been developing these internally since 2015, and they launched the first one in 2016.
And the evolution since then has been completely exponential. Looking at the source material, let's track the immediate predecessors. In 2024, Google released Trillium, their version 6 TPU.
Yeah, and that delivered 4.7 times more performance per chip than the previous generation.
And it was 67% more energy efficient.
Which was huge. Trillium basically proved the ASIC concept could scale. But 2025's version 7, known as Ironwood, really changed the geometry of the data center.
Ironwood was a massive chip focused primarily on inference, right?
Exactly. And to feed data into that processor fast enough, Google had to equip it with up to 192 gigabytes of HBM per chip.
I want to pause on HBM for a second because that acronym gets thrown around constantly in these announcements. High bandwidth memory. This isn't just standard RAM slotted into a motherboard, is it?
Far from it. In traditional computing, the processor and the memory sit on different parts of the motherboard.
Right.
So every time the processor needs data, it has to send a request across a physical wire. That takes time and consumes power. It's basically data travel tax.
And HBM fixes that.
Yeah, HBM actually stacks the memory chips vertically, directly on top of or immediately adjacent to the processor itself.
Oh, wow.
It acts like a massive ultra-fast highway bolted directly into the brain of the chip. You completely eliminate the travel tax.
And Google didn't just build one Ironwood chip. The sources note they linked them together into massive pods of 9,216 chips. They were hitting 42.5 exaflop-ps in FP8.
Exaflop-ps are quintillions of floating point operations per second. It is a scale of math that is genuinely difficult for the human mind to grasp.
Right, and that FP8 designation is crucial too. FP8 stands for 8-bit floating point.
Meaning the precision of the decimals.
Yeah.
When an AI is calculating probabilities, it doesn't always need to know the answer to 15 decimal places.
So by intentionally dropping the extra decimals and using an 8-bit format rather than a 16-bit or 32-bit format, you have the amount of data moving through the system.
Exactly. You trade an imperceptible amount of mathematical precision for a massive doubling of raw speed. And companies like Anthropic and Meta recognized this and started adopting Ironwood at a massive scale.
But even with Ironwood's raw power, Google hit a physical wall.
They did.
Because the math required to build a massive AI model is fundamentally different from the math required to run it for a user. You can't use the same chip for both anymore.
No, you can't. And that realization forced Google to do something unprecedented, bringing us to today's major announcement.
The Generation 8 architecture.
Right. The demands of training an AI versus running inference on an AI have diverged so radically that trying to build a unified chip pretty much guarantees failure. You end up with a processor that is terrible at both.
And that led to the split, the TPU-8T and the TPU-AI.
Exactly.
Wait, in traditional tech, isn't it usually better and cheaper to have one unified chip that does everything well? I mean, economy of scale is everything.
Usually, yeah.
By intentionally splitting their production line into two completely different processors, Google is doubling their research and development costs. They are fracturing their supply chain. Why intentionally take on that massive logistical nightmare instead of just building one really good chip?
Because the physics of the workloads demand it. Let's look at the TPU-8T first. The T stands for training.
Okay.
Building a foundational AI model from scratch is a marathon. You are pumping petabytes of data, essentially the entire written internet, through a system continuously over the course of 3 to 4 months.
And the sources indicate the 8T is built specifically for heavy embedding workloads. Let's define what an embedding is for the listener.
An embedding is basically how a computer understands concepts. A computer doesn't know what a dog actually is. It only knows numbers.
Right.
So during training, the system has to take human concepts, words, and images and map them into a multi-dimensional numerical space. Dog becomes a set of coordinates. Puppy is mapped very close to dog. Car is mapped very far away.
And calculating the millions of dimensions for every piece of human knowledge requires immense brute force throughput.
Yes, and the AT handles that brute force by scaling up to massive superpods of 9,600 chips. It delivers up to 2.7 times better performance per dollar than Ironwood for massive training.
Because during a training run, you don't really care if a specific calculation takes a microsecond or a millisecond, since the whole process is going to take months anyway.
Exactly. You just care about the sheer volume of data moving through the pipe. Its whole purpose is building giant foundational models.
But then you look at the other side of the equation. The TPU-8i, the I stands for inference.
Right, which is focused on post-training and low-latency inference. Inference is when a real human user actually asks the AI to do something.
Which is a completely different scenario. I mean, if you ask an autonomous AI agent to check your calendar, cross-reference your budget, and book a flight, you don't want to wait 3 months. You want the answer in 3 seconds.
You need near zero latency.
Yeah.
And you don't need the AI to read the entire internet again just to book a flight. That brings up the specific architecture the AI is optimized for.
The mixture of experts or MOE models.
Yes.
Let's unpack the mechanism behind a mixture of experts model. Why does running a MOE model require a completely different physical chip?
Well, in an older AI model, every time you asked a question, the entire neural network would light up. Every single parameter was activated to generate the answer, which takes a massive amount of power and time.
But a mixture of experts model is subdivided.
Right, it's subdivided into specialized expert pathways. If you ask a coding question, the AI only activates the coding expert pathways. If you ask a translation question, it only fires up the translation pathways. The rest of the model stays totally dormant.
So the chip doesn't need massive brute force throughput. It needs incredible agility.
Exactly. It needs to rapidly identify which expert to route the query to, activate just that tiny sliver of memory, and deliver the answer instantly.
And the TPU-AI offers up to 80% better performance per dollar, specifically for running those large MOE models.
With near zero latency, trying to build one chip that is perfect at a 3-month marathon of embeddings and also perfect at a 1 millisecond sprint of routing a MOE query. Well, the physical layout of the transistors would just be inherently compromised.
Okay, that answers the why. But the how they are physically pulling off this split without breaking the bank is equally fascinating.
It really is.
Building this bifurcated architecture requires a massive scientific and supply chain ecosystem. The source material dives into the academic evidence, proving just how efficient these TPUs actually are.
Right. Independent studies in Google's own MLPerf benchmark submissions demonstrate that, historically, TPUs achieve 14 to 34 times better energy efficiency in deep learning tasks compared to older general-purpose CPUs and GPUs.
Wait, 14 to 34 times better. When you are talking about gigawatts of power across a global data center network, that is a civilization-level reduction in energy.
It's massive.
How is the chip physically saving that much power?
It comes back to the data travel tax. Because the TPU is an ASIC designed purely for matrix math, the physical distance the electrical signal has to travel in the silicon is microscopic compared to a GPU.
And less distance means less electrical resistance.
Which means less power required and, critically, less heat generated. You don't have to spend as much electricity running massive cooling systems just to keep the chip from melting.
Here's where it gets really interesting. The sources also highlight something called linear scalability, which they've achieved with these massive pods.
Yeah, this is a huge engineering feat.
To understand why this is such a big deal, we need an analogy. Normally, linking thousands of computers together is kind of like a grocery store. Usually, adding 10 cashiers doesn't make the line 10 times faster.
Right, because people still bump into each other.
Exactly. The overhead of managing the traffic creates a massive jam. Adding more lanes actually yields diminishing returns at a certain point.
The networking processors spend so much time figuring out who gets to send data next that the actual computation grinds to a halt.
But with TPU pods, adding more chips actually results in a perfect one-to-one increase in speed.
Yeah, older benchmarks process over 1 million images per second on just 32 devices, and the new chips multiply this exponentially.
They bypass the traffic jam completely. Instead of putting all the chips on one electrical network, they engineered specialized optical pathways. They essentially built a private, high-speed tunnel of light between every single chip in the pod.
What's fascinating here is that reducing energy consumption in data centers via specialized ASICs isn't just about saving Google money. It's practically a requirement for the world's electrical grid as AI scales.
And it isn't just the TPUs doing the heavy lifting. Google pairs these TPUs with their own custom Axion ARM CPUs to handle the general computing workloads.
Right, running the operating system, moving data from storage, that sort of thing.
And the sources note these Axion ARM chips offer 50 to 60% better energy efficiency than traditional x86 equivalents.
Because of the instruction sets. An x86 processor uses a complex instruction set. It handles highly complicated instructions in a single cycle, which takes a lot of power.
But ARM uses a reduced instruction set.
Exactly. Very simple atomic instructions. It takes more steps, but each step uses so little power that the overall energy consumption just plummets.
So they have the optical networking, the efficient ARM CPUs, and the ASICs tailored perfectly for inference and training.
And they aren't doing this alone. Google has deeply diversified their supply chain. They're partnering with Broadcom, MediaTek, Marvell, and Intel.
Spreading the risk and accelerating innovation.
Yeah, they train their own Gemini models entirely on these TPUs to save time and reduce costs compared to a GPU-only approach.
Okay, I want to bring the excitement down a notch here.
Oh,
Well, we've spent the first half of this deep dive exploring a perfectly engineered ecosystem, but building the future of AI infrastructure is fraught with massive vulnerabilities.
that's fair.
This bifurcated 8T and 8I strategy is actually incredibly fragile. Let's look at the roadblocks, starting with a glaring physical vulnerability: the supply chain. Google designs these chips, but they don't fabricate the silicon.
Right. Producing millions of chips on advanced nodes like the upcoming 2-nanometer node relies heavily on TSMC in Taiwan. Any delay from external foundries derails the whole plan.
Google is betting the entire future of their cloud infrastructure on a chip they don't manufacture. If there's a yield issue where the 2-nanometer process gets delayed, this entire brilliant strategy falls apart.
The vulnerability is real.
And even if they get the chips, there's the environmental hurdle. Despite being more efficient, AI data centers are voracious. Sustainability is a massive ethical and regulatory hurdle.
Yeah, the absolute power draw is climbing so fast that efficiency is the only way to physically secure permits to build new centers.
Then there's the software portability issue. Benchmarks show gaps in frameworks like PyTorch, forcing developers to rely on Google's own optimized software like JAX and XLA.
Migrating workloads from GPUs to TPUs is hard. PyTorch doesn't automatically map to a TPU's hardware perfectly. JAX acts as a hyper-optimizing translator, but learning JAX is a huge engineering lift.
So let me ask you this. If you're a scrappy startup trying to build a custom AI agent, does any of this matter to you? Or is this just a playground for billionaires while the rest of us are stuck dealing with software headaches trying to migrate from PyTorch?
This raises an important question, and you're right to be concerned. Google Cloud is trying to democratize access. They want smaller developers to be able to afford the cloud access by renting tiny slices of these massive 9,600 chip superpods.
But the friction is still there.
Yeah, the lock-in effect of the software and the sheer cost of computing power mean the little guy is highly dependent on how these cloud wars play out.
Yeah.
Because Nvidia isn't sitting still.
Right. Nvidia is responding with Blackwell and Rubin. AMD is also entering the fray.
Fierce competition.
But regardless of the roadblocks, the sheer speed of this innovation is staggering. It's bringing us closer to a world where AI assistants reason as fast as humans without ever getting tired.
It really is.
Let's summarize the key takeaways here. Google's TPU 8T and 8I represent a strategic splitting of hardware into training and inference to handle the unique demands of autonomous AI agents.
Right. By utilizing custom ASICs, Axion CPUs, and a diversified supply chain, Google is building a highly efficient, resilient ecosystem to challenge Nvidia's GPU empire.
And why should the listener care?
Well, this fierce competition is relentlessly driving down the cost of computing. Ultimately, that means faster, cheaper, and smarter AI tools for your business or personal use.
It's a race to the bottom for the cost of intelligence. So, what does this all mean? I want to leave you with a final thought to ponder that builds on everything we've discussed.
Okay.
We are currently hyper-optimizing hardware to run specific AI models, like Mixture of Experts. We are physically carving hardware to fit today's software.
Right.
But what happens if the fundamental software architecture of AI completely changes tomorrow?
Well, that's interesting.
Right. If someone invents a totally new way to do AI, do these billions of dollars of highly specialized TPUs become obsolete overnight? Does it prove that NVIDIA's general-purpose GPUs were the safer bet all along? Something for you to think about.